So let's continue the discussion of ideal transformers, and we want to talk about the concept of reflected impedance. So the idea is very simple. The idea is to try to figure out if I have some impedance behind the transformer, how would this impedance look on the primary side of the transformer? What would be the Z equivalent on the primary side of this transformer? Right. So this is kind of like, you can think of this as an act of reflection. So the impedance, so those are dots. The impedance is at the secondary, and the wording that we use is that we say that impedance is reflected to the primary. Right? And it has a certain value at the primary, which is equal to the equivalent impedance, which we can calculate. I mean, all we have to do, right, so we have the V1 here, and then we have the V2, and let's use the convention where the I is coming into the first dot and it's leaving the second dot, right? So with this convention, we can say that V1 over V2 equals N1 over N2, and I1 over I2 equals N2 over N1. Right, there's no minus sign here because we're using the convention where the current enters the dot in the primary and leaves the dot in the secondary. And this is I1, and this current here is I2. Okay, so we want to establish Z equivalent. We know that Z equivalent, or the reflected impedance, is V1 over I1, right? So what is V1? Let's do this calculation. V1 is going to be N1 over N2 V2, right? What is I1? I1 is going to be N2 over N1 I2, right? Now, what is this ZL? ZL equals V2 over I2, right? That's by definition. But we already have a value for V2, right? So V2, we can use this expression here to express V2 in terms of V1, and then that's the trick. We want to express V2 in terms of V1 and I2 in terms of I1. So we need to kind of substitute. Let me do that. Let me do this substitution. So this equals, what's V2? V2 equals N2 over N1 V1, right? And then I2, what's I2? I2 is the inverse, right? Because it's 1 over I2 here. So it's the inverse of N1 over N2 I1. So do some manipulation here. I end up with N2 over N1 squared V1 over I1. So right, okay, and that's the expression, right? This is, of course, equals ZL. So ZL equals N2 over N1 squared. What's V1 over I1? It's Z equivalent, right? So it's Z equivalent. That's what we call the reflected impedance, the impedance that appears on the primary side. I want to write Z equivalent in terms of ZL. So Z equivalent is going to be N1 over N2 squared ZL. This is the expression. So we can write the equations again now, summarize them. we can introduce the constant n. N is defined as n2 over n1. So if we define n, small n, to be the secondary number of windings over the primary number of windings, then we can rewrite our equations. So remember, V1 equals N1 over N2 V2, so V1 equals V2 over small n. I1 over I2 equals N2 over N1, which is n, so I1 equals n I2. And then finally, Z, let's call Z equivalent Z1. So this is a reflected impedance. This is the reflection of the impedance at the secondary side of the transformer over to the primary side. So Z1 equals, let's call it ZL. What's N1 over N2? That's the inverse of N, so it's ZL over N squared. So this is just summarizing the relationships that we derived so far. All right, let's do some examples. Let's do now the first example. Right, the example is as follows. So we have 120 volt, 0 degrees, and then I have I1 going into the circuit. I have 18 ohms, then I have minus J4, a capacitor. Then I have the primary of the transformer, the dot is like this, and then I have V1, I have the core, and then I have the secondary, the dot is inverted. Then I have V2 here. The turns ratio is 4:1, meaning that every 4 turns on the primary corresponds to 1 turn on the secondary. And then I have current I2 going into 2 ohms and J1 ohms. Okay, so we want to solve for the variables here. We want to solve for I1, I2, V1, V2. Right? Now, because here the dot is inverted, right? So remember we said the relationship was V1 equals V2 over N, right? So this relationship holds if the voltage and the secondary follows the dot, right? But the voltage is inverted, therefore we have a minus sign here. And similarly here, I2 is going into the dot rather than leaving the dot. So we have also a minus sign for I2, right, for the current relationship. So I1 equals minus N I2. So those are the basic transformer relationships. Okay. N, of course, is N2 over N1. N2 is 1 and N1 is 4. So this is going to be 1/4. Okay. So what we want to do first, I mean, we want to use the method of reflecting the impedance from the secondary to the primary, right, to solve this problem. Because if we reflect the impedance from the secondary to the primary, the solution becomes easy. Finding V1 becomes easy. V1 becomes just the voltage across that reflected impedance, right? So we end up, if I reflect the impedance, I end up with this circuit. I have the voltage source, and then I have the resistor, capacitor, and then I have the reflected impedance, Z1. Let's call it Z1. Okay. So that's the first step. We want to find the reflected impedance from the secondary to the primary. So Z1 is just equal to ZL over N squared. We established that, right? But N is 1/4, so 1 over N squared. N is 1/4, N squared is 1 over 16. 1 over N squared is the inverse of that, so this becomes 16. And secondary impedance is 2 plus J, right? So Z1 equals 32 plus 16J. Therefore, I1, that's one of the variables we want to solve for, is just going to be the voltage which is 120, over the total impedance, over Z1, which is 32 plus 16J, plus what? Plus 18 minus J4. So this is 32. So 32 plus 18 is what? 32 plus 8 is 40, plus 10 is 50, so this is 50. And then minus J4, 16 minus 4 is 12, right? Plus J12. Do the math here, it turns out to be 2.33 minus 13.5 degrees amp. Okay, so V1 of course is I1 times the reflected impedance. Right? That's what V1 is. So again, let's do it. That's going to be I1 is 120 again over 50 plus J12, and Z1 is 32 plus J16. So do this math again, we end up with V1 being 83.5, 13.07 degrees volt. Okay, and then from V1 we can find V2. V2 is just minus N V1. N is 1/4, right? That's what we said N was, right? So 1/4 of that is about minus, there's a minus sign, 20.87, right? And then the angle remains the same. Now remember we said whenever we write phasors, we prefer to write phasors with a positive magnitude. We don't like to write, typically people don't like to write phasors with negative magnitudes. Right? How do we turn this magnitude into a positive magnitude? We just add an angle of 180, right? Any complex number, just add an angle of 180 to it. Doing that is equivalent to multiplying it by -1, right? So I can remove the minus sign here, but I have to add 180 degrees here. So this becomes 193.07 degrees. Of course, adding 180 or subtracting 180 is absolutely equivalent, right? It gets you to the same number. So I could also subtract 180. So I could get 20.87 minus 166.93 degrees. Right? This is volt. Right? So I could either add 180 or subtract 180. Now the final variable we're trying to solve for is I2. I2 is equal to minus I1 over N. So I2 equals minus I1 over N. Of course, 1 over N is 4, so this becomes minus 4, 2.33 minus 13.5 degrees. That's the value of I1 that we found. So this becomes 9.32. It should be minus, but I'm gonna add 180, right? So this is gonna be minus 13.5 plus 180, so this is going to be 166.5 amps. So we found all the variables we're trying to find: I2, I1, V1, and V2. The next example is an application, right? And the application is the well-known distribution transformer. And power transmission and distribution, like we said, like typically you have the utility, right? Like a utility where they have the generators, right? And then they have all those synchronous machines that generate the voltage, rotating machines where you input fuel, coal or nuclear or whatever. And those machines rotate, those synchronous machines rotate, and they generate a voltage. Right? And what happens is you want to transmit that voltage. So using transformers, you raise that voltage up to very high values. hundreds of kilovolts actually, or even mega volts, right? And then you transmit over long distances, and then you step down into what's called the substation, right? And after that substation, those substations, you know, when you're driving, and then you see a bunch of electrical equipment across the road, with transmission lines coming in and transmission lines coming out. So those things with the fences that typically have wire fences around them are called substations. And on one side of the substation, you have power coming in from the transmission lines, those large transmission lines. And the other side, you have what's called feeders. The feeders are just, you know, those poles. So you have the poles across the street, right? And then you have the wires connected between the poles, the wooden poles. So those this wiring using those wooden poles is called feeders. So those installations are called feeders, and those are typically at a voltage of 13.8 kilovolts, right? So it's still a hefty voltage. That 13.8 kilovolts, of course, cannot go into your house. So what happens is that at the end, when those poles reach the subdivision or the neighborhood or whatever, and they reach your house, there's something called, right? So this is the 13.8 kilovolt. Let me draw it as one line diagram. So there's something called a distribution transformer at the end, and that thing takes the high voltage and turns it to 240 volts, and that goes into your house. Right, where does the 120 come from? Well, the 120 comes from because the secondary of this transformer that goes from 13.8 kilovolts to 240 volts, it's what's called a split phase transformer. So the transformer actually looks like this, if we want to draw it schematically. Right, so it has a primary, it has a secondary, right? So it has 13.8 kilovolt RMS primary, and then the secondary, it drops down the voltage to 240 volt RMS, but then there's a tap in the middle, and there's an extra third wire coming out. And this tap splits the phase, splits the secondary phase. So that's why we call it a split phase transformer. This split phase is each of the split phases is 120 and 120. And this is where the 120 volt comes from. That's why in most homes, in all homes in the USA at least, you do have, sometimes you do have this 240. Many times it's not used, but a lot of the times they are connected. They are used to power your washer or dryer, right? Typically washers and dryers and other such heavy utilities use the 240 volt instead of the 120 because it's more efficient. If you have an electric vehicle, your electric vehicle charger might be running off this 240 volt RMS. Right? So what's the problem here? What are we trying to solve for? Well, the question is, what would the turns ratio be for such a transformer? And assuming that such a transformer doesn't only feed your house, it feeds a bunch of houses. Like, let's say it's not economical to have one transformer per house. Let's say we have like one transformer per 10 houses, let's say. So one transformer feeds 10 houses, and each house is fed by 200 amps, right? Each. So the question is, what would the power rating of this transformer need to be? And what would the primary current IP need to be? That's the question. So let's do it one by one. So N equals V2 over V1, right? That's what N is. Right, because we said V1 equals V2 over N, so N equals V2 over V1. V2 is 240 in this case over 13,800. Right? This is a turns ratio of 0.0174. For every turn on the primary, we have 0.0174 turns on the secondary. This is about like for every 57 turns of the primary, there is one turn on the secondary. Okay. What about the primary current? So let's say we have 200 amps each for each house, and we're powering 10 houses. This is on the secondary. What about the primary current? Well, the primary current, right? So the way to think about transformers is that they always do whatever they do to the current is opposite to what they do to the voltage, and whatever they do to the voltage is opposite to what they do to the current. So if the transformer steps down the voltage, it will step up the current, right? And if you look from the opposite direction, the transformer is stepping up the voltage to reach 13.8 kilovolts, so it's stepping down the current. Right? So the current I1 from the transformer relationship is N times I2, which is 0.0174 times 200 times 10 houses. We have 10 houses, so that's 2,000. If we do this, we discover that the primary current is 34.8 ARMS. Right? So this is going to be a transformer that needs to be able to handle an apparent power of V1 times I1, right? It's a 13,800 times 34.8. If we do the calculation, that turns out to be 480.24 kVA. And that's a typical rating, power rating, apparent power rating for distribution transformers. Typically, they are around that value. I mean, they range from 400 up to 700 kVA. Okay. All right. So the next thing we want to discuss is that when analyzing circuits that have ideal transformers, it is possible for us to use the Thevenin and Norton theorems, right? And under some conditions, they might simplify our calculations or our circuits. Under other conditions, no, they won't, right? But how would you apply those theorems? So it's pretty straightforward. Let's draw like a typical transformer circuit, ideal transformer. Right? So we have a certain turns ratio, 1 to n, let's say, where n is n2 over n1, of course. And then I have some impedance here in the primary circuit. I have some voltage here in the primary circuit. I have some impedance in the secondary circuit. I have some voltage in the secondary circuit. So there are two approaches. We could either divide the circuit here and find the Thevenin equivalent looking into the circuit, or we can divide the circuit here and look and take the Thevenin equivalent looking into the primary winding. Right? So what happens? Let's start with this perspective. Right? So here I'm dividing the circuit into VS1 and then Z1 and then the transformer, and then I'm trying to find the phi Thevenin. Phi Thevenin is the V open circuit, right? I open the circuit, and then the rest of the circuit is here, Z2, VS2, whatever, right? Because I opened the circuit, that means I2 will be 0. This current will be 0 amps. That means the I1 will be 0 amps, right? The relationship of transformer matches, I mean, it still follows. We cannot have current in the primary if we don't have current in the secondary. So there's not going to be no voltage drop on Z1. So the voltage appearing across the primary is going to be VS1. So the V open, the V Thevenin voltage is just gonna, this is 1 to N. Is just gonna be the stepped up voltage. It's gonna be N VS1. That's Thevenin voltage. What about the Thevenin impedance? Z Thevenin. So this is, again, that we know how to do that. We just short the voltage. And now the impedance is just a matter of reflecting the impedance back to the secondary, right? So we know that here what is the looking back, for looking at this problem as reflecting from the primary to secondary. What is, remember we said Z reflected R is Z over N squared, but that's when we reflect the secondary to the primary. Here, the primary is acting as if it's the secondary because we're looking from the secondary, right? So the effective turns ratio here is 1 over N rather than N. So we need to plug in 1 over N here, so this becomes N squared Z. Right? So the reflected impedance from the primary to the secondary is going to be N squared Z. Given that N small is the secondary windings over the primary windings. Okay, think about this. And then, so this is the equivalent circuit, and then we just connect it to the rest of the circuit, Z2 plus minus VS2, right? And then the second approach is to cut the circuit in the primary side, right? And this is going to be Z2 VS2, right? And then this is easy too, so this is going to be, this is 1 over to N. So here VS2, the current is 0. VS2 is going to be, the voltage is going to be stepped down, right? Because we're going opposite, we're going from the secondary to the primary. So the voltage is going to be stepped down by N. So this is going to be VS2 divided by N. And then the impedance is just a matter, Thevenin impedance is just a matter of finding the reflected Z2 impedance. Here we're reflecting from the secondary to the primary, so our equation still follows, which is Z2 over N squared. And then we connect the rest of the circuit, Z1, and then VS1. Right, so can be sometimes confusing following all the divide by N and multiply by N and the sign and all of that. This is just something that will get easier with practice, and there's nothing else to it. Okay, let's do an example of applying Thevenin to a problem with a transformer. Okay, so we have this problem. We have plus minus 12. We have 4 ohms. We have minus J3 ohms. I'm omitting writing the ohms just for brevity. Then I have a dot transformer. Right, and then I have okay. Oh, here the dot is inverted like this. Okay, and then I have 12 ohms, and then J4, and then 48, 30 degrees. Right, and since the problem is to apply the Thevenin simplification from both sides, that's the problem. That's what we're trying to do. So let's do step 1 now. Let's let's do it from this side first. Let's reflect the primary into the secondary. So the first thing is that if I cut this circuit, I2 of course is going to be 0, and then there won't be any current going through 4 and minus J3, so all the 12 volts is going to appear at the primary. Of course, the turns ratio, I forgot to give you the turns ratio. The turns ratio is 1 to 2. Right? So this will take 12 and step it up 2 times, times 2, so it's going to be 24. But its polarity is going to follow the dot. Its polarity is going to be in this direction because the dot is oriented that way. So the Thevenin voltage in this case is going to be flipped. This is going to be 20 compared to this 12 volt. So it's going to be 24 volts because the voltage was stepped up. Right? Now I want to reflect the primary to the secondary. So in this case, it's just going to be the primary times n squared in this case, right? So it's primary times n squared is n is 2, so it's going to be times 4. So it's going to be 16 ohms minus J 12 ohms, right? And that's it. That's Thevenin equivalent circuit. And then I connect the secondary circuit. 12 ohms, J4 plus minus 48, 30 degrees. Okay. Now let's do the second approach where we cut the circuit here. I want to find the Thevenin equivalent circuit for the primary circuit, for the secondary circuit, right? So in this case, again, I1 is 0. This voltage completely appears on the secondary side. Now the voltage gets stepped down, right? It steps because we're going from the secondary to the primary, and n, so we're going from 2 to 1. So there's a step down in the voltage, and due to this dot convention, the voltage flips. So the Thevenin voltage is going to be 48 divided by 2, which is 24. We step up in one direction, we step down in the other direction. And now for the equivalent impedance, I showed the voltage source, and what I'm doing here is I'm reflecting the secondary to the primary. So in this case, I divide by n squared, so I divide by 4. So 12 divided by 4 is going to be 3 ohms, and J4 is going to be just J1 ohms. Right? And then I do the rest of the circuit. Minus J3, 4, and then the 12 volts, 0. Okay. So those two circuits are, equivalent. I mean, this is what we get from doing Thevenin's theorem on either side of the transformer. We can use this circuit to calculate I2 because we reflected into the secondary. We can use the circuit to calculate, so this is here I2, and this is here I1 because we reflected in this case to the primary. So let me write down I1 and I2. Okay. Let's do an example where we do some calculations. Example. Okay. So we want to find VO. To find VO, what do we need to do to find VO for this circuit? Let me draw the circuit. So I have 24 volts, 0 degrees, 4 ohms, minus J4, plus minus 4 minus 90 degrees volt, right? 2 ohms, and then I have the transformer dot here, 1 to 2 transformer, and the dot here, the dots are inverted, and then I have 2 ohms, J3 ohms, and then I have 2 ohms, and then I want to find VO at the output. So this is the VO I want to find. To simplify things, I want to notice that the primary circuit is a bit more complicated than the secondary circuit. So what I could do to simplify things, I could split the circuit here and find the Thevenin equivalent looking in that direction. Right, so what would be the V Thevenin, which is the open circuit voltage? Well, it's going to be, there's no current flowing here, right? Because I opened up the circuit, right? So V Thevenin is going to be a voltage divider between this cap and this resistor. So it's going to be minus J4 over 4 minus J4 times 24, right? But that's not the whole thing. After I find this voltage divider gives me the voltage at this node. The voltage, the open circuit voltage, or the Thevenin voltage is the voltage at this node. So I need to take this voltage and subtract from it this voltage. So this is going to be minus 4 minus 90 degrees. What is an angle of minus 90 degrees, right? It's I, right? It's minus I, right? I has an angle of 90 degrees, minus I has an angle of minus 90 degrees. So this is equivalent, by I mean J, the complex number. Sometimes I mess them up, okay? So minus 90 degrees is equivalent to minus J. So this is equivalent to minus J times 4. So we can do the math. This is going to be plus J4. Let me take that out. 1 minus 24 over 4 minus J4, which is equal to J4. 1 minus 6. 24 over 4 is 6. Over 1 minus J. So if we calculate that, that turns out to be 12 minus 8J, which is 14.42 minus 33.69 degrees volt. Okay, what about the Thevenin equivalent impedance? Well, kill all the voltage sources by shorting them. We end up with just we end up with just actually, I think I made a mistake somewhere. Oh yeah. The mistake I made is that we're cutting up the circuit at this slice, meaning the 2 ohm is included in the Thevenin equivalent circuit. Okay. Yeah, it doesn't make sense to leave the 2 ohm out. Right? It doesn't matter anyway for V Thevenin. Why? Because the current anyway, because we're cutting the circuit, the current in this branch is 0 when we calculate the Thevenin circuit, Thevenin equivalent circuit. So 2 ohms does not matter. Right? The only voltage is going to be this, and the only current is going to flow in this voltage divider. Right? But it will matter for calculating Z Thevenin. For Z Thevenin, we're going to have those two in parallel after we kill the sources, and this in series. So the Thevenin equivalent resistance is going to be 4 parallel minus J4 plus 2, which is minus J4 times 4, 16, over 4 minus J4 plus 2, which is 2 minus J4 over 1 minus J. If we do the math, this turns out to be 4 minus 2J. Right? And we can now redraw the circuit. So the circuit, we found the Thevenin voltage, which turned out to be 14.42 with an angle of minus 33.69 degrees. The Thevenin impedance is 4 ohms. And then we have a negative minus 2J, a negative imaginary reactance is always going to be a capacitor, minus J2. And I have my transformer. And then it goes 1 to 2, and then the dot is down here. Then I have 2 ohms, J3, another 2 ohms, and then VO. This is a resistor, this is an inductor, J3, and then VO. Right? Now we can find the Thevenin equivalent. Now it's simpler to find the Thevenin equivalent on the secondary, because ultimately you want to get one whole loop, one simple loop to solve for VO, right? And this is simple to do. I'm cutting the circuit here in this slice, so the I2 is going to be 0, I1 is going to be 0. The whole voltage is going to appear here at this dot, at this primary coil. Because the dots are inverted, this voltage is going to be inverted, and it's going to be scaled by 2. It's going to be stepped up by 2. So the turns ratio is 1 to 2. So we're going to, the 14.42 is going to turn into 28.84, the same angle, but this is going to be flipped because of the flip in the dots. Now I'm going to reflect the primary impedance into the secondary. And we said when we do that, we multiply by n squared, which is n squared in this case is 4, right? 2 squared is 4. So it's going to be 4 times 4 is going to be 16. And this is going to be 4 times 2, 8. And then I have the secondary side impedances, 2, J3, 2, and this is VO. Now VO is easy to find. VO is just going to be a voltage divider. So it's going to be minus 28.84 minus 33.69, and then voltage divider is going to be 2 over the total impedance, which is 16, plus 2 plus 2, which is 4, which is 20, and then minus J8 plus 3 is going to be minus J5. So this is going to be minus 2.79 when we do the math, minus 19.65 degrees. And we said we don't like a negative sign for the magnitude, so what we can do is we can cancel the negative sign and add 180 there. So we end up with VO equals 2.79, 100.35 degrees. Okay. Now let's do the final example. Okay. So the example as follows. This is an example where it gets a little bit more complicated, because previously we had the primary and the secondary circuits separated pretty much. They are their own independent circuits, and the only link between them is the transformer. But it's possible for us to have some circuit components that connect from the primary to the secondary. So as a circuit exercise, that's something we can solve and we can build even. But typically people don't do that, because the whole idea of a transformer, one big idea for using a transformer, one big reason for using transformers, other than the step up and step down of the voltage and the current, is to provide what's called galvanic isolation. Right? Meaning transferring electrical energy without a direct electrical connection. It's magnetic. So the transformer transfers electrical energy into magnetic energy, then back into electrical energy. Right? So it's a good way to isolate circuits electrically. Okay. So let's do this example where this isolation is broken. So we have 10 volts, 0 degree. I have 2 ohms. I have my primary side, secondary side. The step up is 1 to 2. Turns ratio is 1 to 2. And so I have here plus minus V1, plus minus V2, J2. I mean, up to now it's a typical circuit, but the twist here is that I'm breaking the isolation by connecting an element, a resistor, from the primary to the secondary, like this. Right? Now we want to solve for those variables. So we want to solve for I1 and I2, the current going into the primary and coming out of the secondary, and we want to solve for V1 and V2. So one easy approach here is to do nodal analysis. This is a circuit with two nodes. Oh, one extra thing is that the lower terminals of the transformer are shorted together like this. So this is a circuit with three nodes. It's easy to apply nodal analysis. We have the reference node here, and this is node 1 and node 2. Right? So using node 1 we get the first equation. So let's calculate all the currents going into the node. All the currents going into this node 1 are going to be 10. The first one is going to be 10 minus V1 over 2, voltage over resistance, and then plus V2 minus V1. This is now this resistor over 2, and the current coming in is going to be minus I1 equals 0. This is equation number 1. And then looking at node 2, all the currents coming in node 2 are going to be V1 minus V2 over 2. That's this current. And then I'm going to have plus I2. I2 is going into node 2. And then I'm going to have, what's the current going through this impedance, J2? This is an inductor. It's going to be V2 over J2, but I want to calculate the current going in, so there's going to be a minus sign, equals 0. Right. Now, in addition to those nodal analysis equations, there are the transformer relations. So there are the transformer relations, mainly V2 is going to be a step up version of V1, right? So V2 is going to be 2V1, and I1 is going to be 2I2. Right? So we can plug in V2 into equation 1 and easily solve the equation. Find I1. Why? Well, let's do it. So 10 over 2 is 5 minus V1 over 2, and then V2 we said equals simply 2V1, so it's going to be plus 2V1 over 2, so this is going to be so this is going to be, let me do it completely. So V2 is going to be 2V1 minus V1 over 2 minus I1 equals 0, but 2V1 minus V1 is going to be just V1. So it's going to be V1 over 2. So V1 over 2 cancels with minus V1 over 2, and we end up with I1 equals 5 amps. That's our first solution. And then I2, of course, is going to be half I1. So it's going to be 2.5 amps. Okay. So we're halfway through. The next step is to find V1 and V2, and to do that we look at the second equation. So let me rewrite it. Let me send V2 over J to J to the other side, so this becomes V2 over 2J. I sent it to the other side, but I know that V2 equals 2V1, so this is going to be V1, right? Instead of V2, 2V1, 2 cancel with 2, right? And then this equals I2, and we know I2 equals 2.5. And then V1 minus V2 over 2. So this is V1 minus V2 over 2. But we know that V2 is just 2V1. So it's going to be V1 minus 2V1, which is minus V1 over 2. Plus. Right, this is an equation in one variable. We can easily solve for it. Let me multiply everything by 2. So minus V1 plus 5 equals minus 2J V1. So I end up with, if I take V1 to the other side, I end up with 1 minus 2j. V1 equals 5. So V1 equals 5 over 1 minus 2j. Right, and this equals 1 plus 2j. So V1, what's the magnitude of this? Let me turn it into polar. So it's going to be 1 squared plus 2 squared, which is 1 plus 4, which is 5. Square root is going to be 5. Square root 5. That's the magnitude. And then the angle is going to be 63.43 degrees. It's arctan 2 over 1. Okay. V2 we said is just comes from the transformer relationship, right? V2, where did I write it down? Yeah, V2 is just 2V1. So V2 is just going to be 2 square root 5, 63.43 degrees volt. Okay. So as part of homework 3, I'm going to add a couple of problems from this chapter. I got a request to extend the deadline, which I will, for homework 3, which I will do once I get to it. So soon, I'll do it soon, like today or tomorrow, but I'm gonna still add a couple of problems from this chapter into homework 3. Alright guys, so we'll continue next time. We're done with this chapter for now. At this point, we're done with this chapter, and now we're gonna move to the next chapter, which is, I believe, three-phase circuits, polyphase circuits. All right, thank you guys.